Okay, so now that we have seen how to compute conjugacy classes in Sn and the sizes of the conjugacy classes in Sn, let's see some related things that start to go more in depth into the theory of the symmetric group. So one thing I would like to tell you about are centralizers in Sn, how to compute the centralizer of an element in Sn. So remember, if we have a G a group and X in G, we have the centralizer in G of X. This is the set of all G in G such that Gx equals Xg. So, or another way to say it, it's the G in G such that Gxg inverse is equal to X. So we said that this is the stabilizer of X for the action of G on itself by conjugation. Okay? And remember that we saw all of these notions, stabilizer, orbit, conjugacy classes. We saw all of this come together, well, in the most general setting in this orbit stabilizer theorem. But in the case of conjugation, we had this class equation that brings these concepts together. And so we can see this in action in the case of the symmetric group. So let's take, for example, X is 1, 2, 3, 4, 5 in S5. Okay. We might want to know what are the permutations in S5 that commute with X. Okay. So question, what is centralizer in S5 of X? Okay. Now, whenever we have an element in an arbitrary group, there's one thing that we always know is trivially contained in the centralizer. We know that the powers of an element always commute with that element. So we always have that the subgroup generated by X is contained in its centralizer. And so in this case of the symmetric group, what that is telling us is, so we have X is contained in the centralizer S5 of X. And we know that the order of X, which is the order of the subgroup that it generates, is equal to 5 because X is a 5 cycle. Now, is there something else in the centralizer? Well, so is there something else in Okay, let's find out. So what's first of all, what's the size of the conjugacy class? That's the orbit of X. So if I look at the class in S5 of X, then by the previous lecture, and just so that we get used to the language of group actions, let's remember that this is also the orbit of X under conjugation. This is nothing else than the set of 5 cycles in S5. And so, how many of them are there? So we discussed last lecture in the case of S4 how to count this. Number of cycles is easier to count than number of elements of some more complicated cycle type. So this is just 5 factorial divided by 5, dividing by 5 for the 5 ways to cyclically reorder a 5 cycle without changing the underlying permutation. And so this comes out to 4 factorial, which is 24. Now, we know that by the orbit stabilizer relation, so let's remember that this is the stabilizer in G of x for conjugation. By the orbit stabilizer, we know that the centralizer in G of x, well, we know that G modulo the centralizer is isomorphic to the class. This is just writing the orbit stabilizer for conjugation. This is as G sets. So now the order of G divided, and let's now put G equal to S5. So the order of S5 divided by the order of the centralizer in S5 of X is equal to the order of the conjugacy class S5 of X. And this thing we just computed to being 24. The order of S5 is 5 factorial is 120. So from this equation, we get that the order of the centralizer in S5 of X is 5 factorial divided by 4 factorial is 5. But we already had 5 elements. Okay? So that what this is telling us is that there is nothing more. So the answer to this question, is there something else in the centralizer, is no. The centralizer in S5 of X is equal exactly to the subgroup generated by X. That is, it is the subgroup generated by this 1, 2, 3, 4, 5. Okay. Okay. So we've seen a simple example of computing the centralizer in the case of this 5 cycle in S5. Now let's do a more sophisticated example where we will get a bigger centralizer than just the subgroup generated by the element itself, which was what happened in the first example. And also, as you will see in a moment, we will be faced with the problem from the orbit stabilizer. We will know the size of the centralizer, but we will have to go out and search for new elements besides those in the subgroup generated by the element that lie in the centralizer. And that's an interesting problem. So let's do the example where we now take our element y to be the product of these two cycles. And now I think of this not in S5, but in S6 to make things a bit more interesting. And let me also just introduce notation that's very useful. Instead of saying 2 cycle over and over again, since here we have a product of 2 cycles. A 2 cycle is called a transposition. So y is a product of 2 disjoint transpositions. You might wonder why we make a big deal out of recalling this thing that's short to write and writing this long word instead, but this is much more convenient. I don't know, once you get used to this language. Anyway, so we are interested in what is the centralizer in S6 of y. So as I was telling you, and as we saw in the previous example, we know that the subgroup generated by y lies in there. But this has not really advanced us much because the order of y is equal to 2. And we can, since we are computing here the order of a permutation, we can make a remark about what happens in computing the order of a permutation in general. So if sigma is in Sn and sigma is equal to sigma 1 up to sigma m product of disjoint cycles of lengths k1 up to km, then the order of sigma is the least common multiple of k1 up to km. In our case, y, we have product of two transpositions, so we have k1 and k2 both equal to 2. The least common multiple of 2 and 2 is 2. So it's a bit of a boring example of this remark, but another example would be to take the element z is 1, 2 times 3, 4, 5. Here, the order of z would be the least common multiple of 2 and 3. It would be 6. And a word of caution, so here we have somehow two extremes. Here they are relatively prime, our cycle lengths. Here the cycle lengths are the same. So here you just multiply the orders for the least common multiple. Here it's just the common length of them that is the common multiple. But we can do a more complicated example, which would be to take W is equal to, so if I want a more complicated example, I should think of two numbers where it's a bit more complicated to think of their least common multiple. The simplest example is 4 and 6, whose least common multiple is 12. So if I take a product of a 4 cycle, 1, 2, 3, 4, times a 6 cycle, 5, 6, 7, 8, 9. So I have 1, 2, 3, 4, 5, and 10. So this is of type 4, 6. And so the order of W is the LCM of 4 and 6, which is 12, even though their product is 24. That's because they share 2 as a greatest common divisor. Okay, let's get back to our original question, what is the centralizer of y? So y itself and the subgroup that it generates just gave us two elements. From the orbit stabilizer relation, we can quickly compute what the order of the centralizer is. So the order of the centralizer in S6 of y is equal to, by orbit stabilizer, it's the size of S6 divided by the size of the class in S6 of y. Okay, now what's the size of the class? Well, we know by what we said about conjugation in the symmetric group, this is the number of elements of the same cycle type as y, cycle type 2, 2. So this is equal to 6 times 5 times 4 times 3. And now I do not continue. Beware, I do not continue 2 times 1. It's very easy to make this mistake of just going on and writing just 6 factorial divided by stuff. Okay, I should also say there are many different ways of computing these orders, but for my way, I'm saying this is these 6, 5, 4, 3. This is for the first, second, third, fourth element, and then I divide by 2, 2, and 2. The first 2 is for cyclically permuting inside this transposition, the second 2 permuting inside this transposition, and the third 2 is for permuting between the 2 transpositions, because they are of the same type. Remember, we said that for z, we would not do an additional division by 2, because if I flip this, then it's 3, 2, not 2, 3. For the counting argument, this is significant. Okay, so now we do this division. So this 4 cancels out with these 2 2s. And this 6, the 2, I have a 3 left. So the size of the conjugacy class is 3 times 3, which is 9, times 5 is 45. All right. On the other hand, I know that the size of S6 is 6 factorial is 720. So by the relation that I have on that top board over there, I can now obtain the size of the centralizer. So this is equal to 6 factorial divided by 45. And notice I prefer not to write out the actual numbers, but just their factorization, because now the division is going to be much easier. So what I have left after crossing things out is 2 times 4 times 2 is 16. So the centralizer has 16 elements. I want another word of caution. You might ask yourself, why am I being so pedantic and writing these subscripts S6 everywhere? Okay. And in fact, much of the time we sort of drop these. But one reason to do this is that you can work out for yourself that if I look at the centralizer in S5 of y, this does not have the same order. This only has 8 elements. Okay? So it's important to specify in which group we do the centralizer, especially when we have an element that makes sense in several groups at the same time. Okay, good. But so now we have 16 elements in the centralizer, and so far we've found only 2. So we have a long way to go. So this is going to illustrate now how do we find elements in the centralizer beyond the initial idea of the subgroup generated by the element itself. So one idea that is useful is, so idea 1, is disjoint elements commute. How is that helpful to us? Because our element is 1, 2 times 3, 4. There is a permutation that is disjoint to it, namely the transposition 5, 6. So 5, 6 is disjoint with y, implies 5, 6 is in the centralizer in S6 of y. On the other hand, about the exercise / remark I made over here, this element 5, 6 is not in S5, so it's not in the centralizer of y in S5. There you see the difference between the S5 and the S6. Okay, good. So once we know this, then we know, in fact, that the subgroup generated by 5, 6, and y, this is contained in the centralizer. Okay? And because they commute and they both have order 2, this group is isomorphic to, let's write it over here. Let's give this group that we found a name. Let's call it V. And V is isomorphic to Z mod 2 times Z mod 2. Okay? It's an abelian group of order 4 that is not cyclic. We need, we need 16 elements. So now this idea of disjoint elements commute is not enough. So it's important to note that, so caution, the converse of this is not true. So elements may commute while not disjoint. It's a bit more difficult to motivate how you find ones that are not that are not disjoint, that commute with one another. So at this stage in the game, maybe it's best if I just somehow reveal a secret to you, that if you try multiplying out 1, 2, 3, 4, which is y, and you take these 4 numbers, but you now permute them in a different way to get another product of 2 disjoint transpositions, like 1, 3, 2, 4, or the other way I can do it is 1, 4, 2, 3. So these are the 3 elements of type 2, 2, and S4, and you check these all commute with each other. And they're kind of famous because if we put them together, and we call W the subgroup 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3, we get a subgroup of S4. It is isomorphic to this V. Remark, W is isomorphic to V, and the nice thing about it is that W is a normal subgroup of S4. That's why it's famous. All right, but okay. So this this little secret is giving us more elements in the centralizer because this 1, 2, 3, 4 is Y. So we have W is contained in the centralizer in S6 of Y. Okay, so that implies that W, the subgroup generated by W and by V, all of this is in the centralizer. Okay, they each have order 4. We have to be careful here. We can't just say 4 and 4, so they generate a subgroup of order 16, because in fact they have an intersection, right? For example, the element Y is in their intersection. This group, let's call it T. The order of T is 8. So T is generated by Y, by the transposition 5, 6, and by, I can take another one of these, 1, 3, 2, 4. So it's in fact generated just by these 3 elements, and these 3 elements generated kind of like a basis in a vector space. Okay, so this is why we have 8 elements. But this order of the centralizer is 16, so we're still on the lookout for another 8 elements. Okay, so we have gotten up to 8 out of the 16 elements in the centralizer, and we have used 2 things. There was idea 1 about disjoint cycles commute. There was then the idea 2 was just it was not an idea so much as the existence of this subgroup W that is sometimes called the Klein 4 group. Okay, now we need a third idea to make it home, and this is a general idea that is useful. It's kind of going back to the idea 0, which was to take the subgroup generated by the element. If our element is the square of some other element, okay, then our element is in the subgroup generated by that square root. Okay, we should be careful about doing square root in a group, but if we find an element whose square is y, then the whole subgroup generated by this element will also be contained there. And things are looking good for us because, so let's call this in quotations square root of our element. So that is, find b such that b squared is equal to y. This may or may not be possible, okay? For example, if our y was just a transposition, it would not be possible. But things are looking good for us because y is equal to 1, 2, 3, 4. It's a product of two disjoint transpositions. If you've tried to square and cube and take powers of permutations, then you might have noticed that what happens is if you start from an n cycle and you take powers of it, you will encounter things that are a disjoint product of d cycles where d is a divisor of n. In particular, here when we have a product of two disjoint transpositions, this suggests to us to try to find a fourth cycle whose square is y. And so we want, so we look for a fourth cycle. And okay, so now if we could try, just to see how this works, we could try our favorite fourth cycle, 1, 2, 3, 4. This won't work. What happens here, we get for the square, when you square, you sort of skip one, so you get 1, 3 times 2, 4. So this is no good. On the other hand, it suggests what to do. So now try b equals, so we have the 1, and we want it that after we skip 1, we get the 2. So we want 1, 2, 3, 4, like this. So I do 1, I skip 3. I want that I skip 1, and I get 4. So now this is good. So now b squared is 1, 2, 3, 4. Good. Okay, good. So now b commutes with y, because y is a power of b. So b is in the centralizer in S6 of y. And so this implies that I can take the subgroup generated by b and this subgroup T that I had before, that this is in the centralizer. Okay, and now B is not in T. Why? For example, because every element of T has order 2, while B has order 4. Okay, so B is not in T. This implies, by Lagrange's theorem, if it's not in there, the subgroup that they generate, so it has more than 8 elements, and the number of elements has to divide the order of the big group, the centralizer, which is 16. So it must have 16 elements. So this implies that the subgroup generated by B and T is the full centralizer. Okay? So let's conclude. We have that the centralizer in S6 of Y, this is generated by the elements. So I have, if I want to write them out explicitly, I have this, so I have Y itself, which is 1, 2, 3, 4. I have another one from this Klein 4 group, 1, 3, 2, 4. That gives me W. Then to get T, which order did we do it in? No, wait. T, well, anyway, I have this one from the Klein 4 group. I have 5, 6 because it is disjoint to the ones before. And finally, I have my B, which is the 4-cycle 1, 3, 2, 4. OK, good. So we found a description of the centralizer. Note that we don't have to write down all 16 elements to understand what's going on. It's enough to give these generators and to understand the relations between them. To do that, let me just note that if you look at the subgroup of the centralizer S6 of Y generated by, if I leave out this 5, 6 that's disjoint, and I just look at the one that is generated by 1, 3, 2, 4, this 4-cycle and 1, 2, 3, 4, and 1, 3, 2, 4, this is isomorphic to D8 dihedral of order 8. And then the big centralizer is just the direct product of this dihedral group of order 8 with this subgroup of order 2 generated by this disjoint 1, 5, 6. Okay.